Hi, my name is Trainin from the University of Nebraska-Lincoln.
And I'm Kimberly Ingraham-Beck from Gretna Public Schools.
And this is CS4NE. And today we've got a great interview for you. We're talking to Abby Langner.
Yes. So she was on previously talking to us about pair programming. So today she's going to talk to us about physical computing.
All right. So we're getting a lot of physical computing lately. And I've been thinking about this because it's really an entry point for students to get into computing. As we're shifting to having everybody participate in computer science, we really want to make sure that there are lots of avenues in. We talked about art, and we can talk about music, and this time we're talking about physical computing and different strategies, working with high school students who may have zero background in computer science. So let's go to the interview.
Well, hi, Abby. Thanks so much for joining us. Remind us who you are and where you teach.
Hi, thanks for having me. I am Abby Langner, and I'm teaching at Westside High School in Omaha. This is my third year there, but quite a few more years as an educator in general. So, yeah, that's where I'm at and what I'm doing. I teach infotech, IT fundamentals, web design. Next year, we're starting our cybersecurity class. So yay, I'm very excited about that. We're growing that program pretty well, and I'm happy to be a part of it.
Could you tell us why physical computing is important and a little bit about what it is?
Sure. Physical computing involves having hardware devices and programming environments. So it's more like a holistic system. The Big Book of Computing Pedagogy from Hello World describes it as taking real-time inputs from the environment and then processing them on that device to produce an output. So typically you'll have a sensor bringing in your input or some peripheral like a keyboard or a controller or something like that. And then the student is responsible for something in the middle of that black box to actually process it. And then there's an output with like motion or lights or a printout or something like that. So it's a pretty broad term. If you generalize to like an input-output machine, you're talking about most computers, but also any robot or, like I was saying, certain peripherals will work, and lots of different electronics. So that's what it is. There are certain elements to a high-quality lesson about physical computing where you'll have examples, you'll have some hands-on tutorials, and you'll also get students to tinker a bit with it. Some of these benefits of doing this are that you have complete systems. This is something that sometimes gets left out when things are modularized and packaged in ways where maybe you're just doing a programming unit or you're just doing a hardware unit. This brings it all together. You have a certain piece of hardware that you are manipulating. You are using the environment to manipulate its outcomes. So having that holistic system, then of course the hands-on engagement is highly motivating. I use a lot of different robots with especially my computer science club, and we explore it in IT fundamentals, and we get a lot of excitement for that. So when students can work hands-on with a physical device, there's a lot more excitement and engagement in that. They also develop some creative design skills, especially depending on how much of the actual building of the device they do. So if it's a robot they have to build from scratch, they get a few more benefits of design skills from that. But there's pros and cons to that too. And we'll get there. And then, of course, it provides those concrete, like real world applications. Who doesn't love talking about robots out there in industry or in science or in engineering?
Absolutely. Yeah. So how do you see physical computing connecting with broader CS standards and pathways? You've talked just a little bit about this, but anything more you want to elaborate on?
Right. So it's a pretty quick step from, say, using a peripheral like a game controller and mapping those controls and getting interesting inputs and outputs from it to then going to game dev. There's also a lot of potential for taking those holistic systems and then going to the next level in, say, web design, where you have a web server that you are managing. So you're not only building the website, but you're managing the server it's running on. So there's a pretty much the sky's the limit. Since most computing devices will qualify as physical computing, you've got pretty much any path you want to take. We can find you a device that'll get you there.
That's awesome. So speaking of a device, how do you recommend choosing where to start if you want to bring physical computing into your classroom?
First of all, start with what other people you trust are doing. Start with anybody else in your building you can work with. Start with somebody you know that can tell you for real what it's like working with a certain piece of hardware. So if you are in a collaborative group like CSTA, maybe you have some connections there. Or if you're in a building fortunate enough to have a team to work with. For example, in my building, I have probably 4 or 5 different people that we might collaborate on using the same bit of hardware. For example, I'm borrowing the Ozobots from the instructor who's doing AP computer science. I think it's CSP. He's using the Ozobots with those, and I'm going to borrow them for IT fundamentals. And so we have that option of just kind of leaning on each other. So as far as starting points go, 100% go with somebody you know if you have that resource, and reach out to us, especially through our groups like CSTA, and go with that. Otherwise, there's lots of potential considerations for where to start. So if you have a blank check and you get to start wherever you want, well, maybe blank check is the right word. Cost is one of those things. Things can get expensive fast in physical computing. When you're buying hardware, it can go up pretty quick. However, there are other low-cost ways to get started, even with expensive hardware. You can borrow some. Like I said, we're borrowing some across our building. You might also be able to borrow from, say, a lending library. Like at UNO, I believe Dr. Dorn was in charge of the PK-12 lending library, last I knew. And then, I believe NPPD has some gear, and there might be other industry that is willing to do that. I actually did I did the NPPD professional development over the summer, the STEM professional development that went across 2 days. And that was awesome. It was all physical computing. And then not only did we get the information about potentially borrowing some, but there was a little shopping spree at the end. So we all got a little gear. Mine literally arrived at school today. I'm so excited. My microbits have arrived.
Awesome.
So yeah, cost is a thing, but there are ways to get deals, freebies, borrow stuff. Also consider if the thing you are getting has some trade-in value for upgrades. Certain pieces of hardware may have that opportunity. Certain robots, especially like the self-contained units like Ozobots and Spheros. I've heard of those doing it. Never actually wanted to trade mine in yet, so I'm still kind of working on those. But eventually I'm going to want to upgrade, and yeah, I'll start looking into those. So if you know that you're in it for the long haul, you might want to look at that. Otherwise, yeah, like cost is a thing, of course. What else? One thing to consider is the level of like building the hardware and the level of electrical work. Because DIY is very fun and there's lots of great benefits to the students. It's very engaging, hands-on, they get that design experience, but also it takes time. Things can go wrong. It's a whole extra level of debugging. It's a whole extra level of mess. You may not have lab space for something like that. And it may involve other skills that are not necessarily in scope or that you have time to teach. For example, I love wearables. I've done sew and code workshops, but that means I have to also teach sewing skills. And I don't always have time for that kind of thing. So think about how much of the building it, how much of the electrical work you want to do, Think about how you would manage that lab and not only the mess of it, the safety of it, and how you're going to manage it as a classroom teacher. So there's every level in between, or every level of this. So you've got self-contained units like those Spheros or those Ozobots, or peripherals like your game controller that you just plug into the computer you already have. There's also certain intros to electronics that are really useful. Snap circuits are really popular. And then you can start getting into what you might call real electronics, wires, breadboards, everything. You can have some assembly required, like a microbit, which has some things built into the microchip that are immediately usable out of the box, but also lots of extensibility. Or you could have like completely all assembly is required, like a Raspberry Pi, and you have to really put the whole thing together. So yeah, I think I also talked about lab safety. So the level of DIY that you're willing to go for here, and that might depend on exactly which class you're teaching. If you're just doing a quick intro, you might want a self-contained unit. If you are doing a robotics class, you're probably going to do a lot more DIY because you're going to be building that robot, or at least building some of your robots. So that's one thing. Also, another consideration, we did cost, we did level of DIY. There's also the level of programming experience that these kids are going to need to have in order to do this. So some of them I have this really hot take about remote control, because some people throw a lot of remote control into robotics, and I'm always like, but a robot is an automaton. So that is my hot take, is RC doesn't quite count. It's so close because you have your controller input, but depending on how much of the student is actually doing that black box in the middle, like how much of the student is controlling that processing in the middle before the output happens. So Ozobot, which I know and love, and I swear I'm not shilling for Ozobot, they have an app, and in the app you have the option of just doing RC with this bot, but that program's already written. The student's not writing the control program for it. They're just controlling with like a joystick. And that's not physical computing. The student's not doing any of the computing part of it. They're just controlling a controller. So that would be the lowest level of programming, right? And then you've got things that are more like a set API. So Ozobot's about to grow with me here, where there is a certain, it's got a line following program. If you've never seen an Ozobot, it's got a line following program that's its default program, and it can read color codes to make it do stuff along that line. And so that's the part where the students start programming. It's a set API of color codes, and the students pick which ones to do in what sequence. Very simple bit of programming, kind of low level. Almost all of it is just sequential coding. But then it also has block programming. So you can move beyond that default program. And that's where a lot more of these other physical computing are about to jump in, is either block programming or text programming, that you then have the student doing that computing piece of the physical computing. So there will be some programming involved if you're doing physical computing. But what level you want to do that at is entirely up to you. Think about not only the level of programming, but what environment is that programming going to be done in? And how are you going to transfer programs between your primary workstation and the physical computing device that you're trying to put the controlling program on? Another one is the ecosystem. So when I say ecosystem, I mean what all is available for that device to be more extensible. So this is one place where my Ozobot has a disadvantage because it's a self-contained unit. There's not a lot you can add to it. Whereas, say, a microbit, which has pinouts that you can then connect pretty much anything to. Similarly, one I haven't mentioned yet is Adafruit has, I think, Circuit Playground, which I'm pretty sure code.org has some lessons for Adafruit's Circuit Playground. So there's an ecosystem where if you're already using code.org for stuff, maybe you want to look at what they offer for physical computing and consider those devices. Same with like CodeHS or any other environment, platform, if you will, that has kind of a variety of curriculum. If you are already using a curriculum from a provider like that, check out what they prefer you would use. What do they recommend? What lessons do they have? Because if you're already comfortable in that environment, awesome. That's a wonderful place to start. And then I think the last point about ecosystem is about replacement parts, warranty, and returns. Classic buying stuff, especially when there's a higher risk of things breaking because it's delicate electronics.
So finally, what advice do you have for teachers who want to add a physical computing component to their work or to their students' work?
Excellent question. So start small and start with, like I said earlier, tap people who you already work with, who you already know, who you professionally network with, to find out what is working for them. They might be able to help you out with your particular classroom setup, class sizes, the ecosystems you already know you're working in. Getting advice from somebody you know will be really good, and then picking one lesson or one sensor on the device to focus on, or something that can help you downscope, so you're not sinking a ton of time into it the first time you do it, because you will definitely learn some things hands-on that no one can really prepare you for. I think one of the things that caught me off guard the first time I was doing physical computing with a whole class was the lab safety part. And that taught me real fast to go small when I'm starting, especially in those first lessons with my students when they're not used to lab rules yet.
Absolutely amazing advice and such good insight into doing this. I can tell that you has done this before and you've given so much thought to it. So thank you so much for joining us. I really appreciate you taking your time to talk to us.
Yeah, thanks for having me. Love to help out anytime.
All right. So that was a lovely interview. What were your biggest takeaways?
So one thing I really love about physical computing that Abby touched on is that it reinforces the concepts kids are learning about. And so, learning how to code a for loop is good, but seeing how a for loop makes things react, a robot, a microbit, an ozobot, whatever, it is different. It's tangible.
Yes.
And so I really like physical computing for that
From
reason.
that perspective?
Yeah.
All right. And what I liked is the idea of multiple touch points. So you've got your basic classes where you're doing some physical computing, you're doing some really foundational stuff, but then adding to it more advanced classes, coding competitions, and creating that ecosystem that you can just have one touch, which is required now, or you can have the opportunity to interact and grow and do more and more if that's the direction you're interested in.
Absolutely. All right. Well, thank you so much for joining us. This was CS for Any.